Well, good afternoon, everyone, and welcome. It's my great pleasure to introduce today's inviter speaker, Professor Jean-Baptiste Poline from McGill University. Before I begin, I'd like to thank CIBM for hosting this event and for their generous support, which makes all these gatherings possible. Professor Poline, or JB, is a tenured professor in the Department of Neurology and Neurosurgery at the School of Computer Science at McGill, where he directs the Origami Lab, which is a neuro data science laboratory, right? And his group, as he will show, I'm sure, develops cutting-edge tools such as NeuroBagel and NiPoppy, which aim at improving data integration, accessibility, and in general reproducibility in neuroimaging. And I'm going to cut my introduction short because Jebe asked for it, and say that please join me in welcoming Jebe, a great scientist, and I'm sure he will give a very inspiring talk. Thank you so much, and welcome.
Thank you very much. Have the move slides. Yeah, so I go by JB, as Oscar said. So if you want to address me, if you feel like you're coming up a little bit more closer to the things, if you don't, that's okay. Please also interrupt me. And I don't know how the Zoom people can interrupt, but please raise your hand on Zoom, and I'll try to watch, and so that we can make that more of a conversation than a formal talk. So please don't hesitate. I know that people do hesitate, but I'm trying to get the conversation going. So this is my lab plus some friends. You will see like a couple of people that are close to the NIPREP world of Oscar, Chris Markiewicz, Yari Kachenko, and a couple of other people there. This is my kind of a retreat. Sort of in the winter, we go to the winter. We do a retreat in the winter. One of the I was wondering if I could actually see the slides on that computer as well. No, okay, let's forget about that. Let me just move it a bit so that. One of the the reason of the work of the lab has been a bit of a frustration aspect, and the frustration is that there is a huge number of papers being published, really, and that number is increasing. You know, the rate of increase is still linear or exponential, depending. And there are reasons why, and I can go back to that. But there is clearly a sort of a mismatch between the number of papers and the kind of a progress that is being made in some area of science. That is one of the papers that is describing that mismatch. And in general, I guess there's some kind of the feeling of in the scientific communities in general that there's a lack of efficiency of our work in research, or sometimes a bit about this is side things. And I'm going to try to reintroduce, for those who have never heard, but I'm sure you all have, but at least we make a bit of a background on reproducibility in neuroscience/neuroimaging, and still a bit why there is a possible problem, and then what is the gap that we should fill, and then present a couple of work that we've done in the direction of trying to cope for that reproducibility problem, but also more like in general increasing efficiency aspects. I think that's the. So I'm pretty sure that many of you, at least have heard about that paper that is called the Why Most of the Research Publisher Findings Are False. It's an old paper from Ioannidis. I think it's a statistical argument. It's not like an experimental argument, but I think it's still worth kind of considering the statistical argument. And in general, even in the Lancet, there was some feeling that things are not I love the quote, I think, from the Lancet editor. Lancet is a pretty conservative kind of journal, and it says that our love for significance pollutes the literature, and we're making up stories a little bit more friendly. So there's a sense, even with the most conservative and most sort of solid sort of editors in journal, that there's kind of an issue in that thing. My own kind of a word, or this paper was interesting to see that this, it was a meta-analysis of about 100 studies that were, in the unipolar depression thing, and seeing whether there's a consensus in terms of what are the brain regions involved in unipolar depression. And after that meta-analysis, and it was a well-done meta-analysis, there was no consensus in that in the meta-analysis, which means that there is 100 or so studies that have been published with significant results showing that some brain regions are being involved in things, and still we don't have solid information from those 100 studies. NIH, when NIH was NIH, I guess, but had a plan for reproducibility, and data sharing was one of the key aspects of that. And I think that's so what's the gap? What are the gaps? I think one of the principal gap, I think Oscar, you were very much involved in that study, which is what I call the analytical flexibility. So how many people have not heard about that study before? Because I want to go quickly if everyone has heard about it. Who has not heard about that study? I guess half of the room. So let me briefly describe it. It's one data set, an fMRI data set, sent to 70 laboratories. With the task to analyze that data set in the, such that you have to then ask whether, that hypothesis, which is whether that condition is actually eliciting some brain regions, significant brain regions, is actually, had to be rejected or not. And so in that kind of you got 70 labs, so that kind of a matrix here has a 70 labs on each side. The big kind of reddish area is the areas where images coming out of that bold so fMRI contrast were, correlated in a positive way. And I say correlated, but in a positive way, but, most of those correlations were more like, 0.5, 0.6, 0.7, 0.8, like it's not 0.99, like, everywhere, like, it's then there was another 10 labs that show anti-correlated results. And then there's another 10-ish labs that show like, more like a noisy things, right? So I think if you can read those things, that's. But even if you look at the 50 labs that showed like correlated results in their contrast, you see that there's even when you take the decision whether yes, condition A was greater than condition B in some region of the brain, then you have like 40% that say yes and the 60% that say no, and that's basically not far from like random results in some sense, like so in that decision aspect was very noisy aspect. That was fMRI, but the same sort of studies were done with, for instance, like extracting tracts of the brain with diffusion imaging, and you see if you send the same data set to like many labs in that respect, you also find like a very different kind of tracks that are going to. So that's a very valuable result there. In kind of an anatomical sort of a world, like when you look at cortical thickness, subcortical volume, and so on, you also find the same sort of differences, like very variable results. And that's again, also in all areas of brain imaging, we see some kind of very high level of variability when you change the analytical aspect. And how many papers do you see are showing results from, like, say, 5, 6, 7 pipelines? I would say, like, almost none, except those 70 pipelines that were used for one data set on the NARPS experiment. So there are a couple of problems. One of the problems of reproducibility could be a data set shift. So you do a study on one data set, then you try to reproduce or generalize that study on another cohort, and maybe it works, maybe it doesn't. So that was a study that was done by one of the postdocs at the lab, in the lab at the time. So Jerome looked at the UK Biobank, learned whether subjects were, let's say, smoking or had some disease, or learned some of the characteristic of subjects, in the UK Biobank, but learning on the subpopulation that maybe are the young subject or the old subject or the female or the male and so on. So, you know, kind of looking at a learner that would be, you know, like a trained on a specific subcohort, and then looking at how much do you lose of the accuracy of that prediction when you apply that on another cohort, on another shifted data set in some distributed, like, you know, statistical way. And what the result of that study, which I will describe in detail, but the result of that study is basically you lose a lot of the accuracy when you actually shift the data. So meaning, like, you know, whatever, and, you know, we're talking about also ethnicity, we're talking about, you know, like a social background, we could, like, you know, anything that's, you know, that shift possibly the dimension of the cohort might actually, you know, affect the generosity of your results. Another problem, which is, I love that problem. It's a very old slide, but it's very kind of still very so useful to think about. So this is the relationship between the BDNF and the cortex and the volume of the hippocampus. So that on the x-axis, you've got the year of publication, and on the y-axis, you've got the strength of the connection between BDNF, you know, the genetic variant. And the hippocampal volume. So what happens here is that in the early days of publication, you see very high kind of effect sizes. So that's the Cohen-D effect size of that relation. And then, you know, as with small cohorts, so the size of those circles here are the size of the cohort, the sample size. And then when you look at, you know, later publication, you said that larger cohort, the sample size is going down. That's a very, very generic, very general result. That result, I can tell you, is very reproducible. It's and to the extent that we don't know whether there is still, like, you know, an actual, you know, link between the hippocampal volume and BDNF. In the machine learning kind of literature, there is a work of Galvarco here, for instance, shows that same sort of effect is kind of occurring as well when you look at trying to predict diagnosis of a specific cohort, and you look at that prediction and as a function of the size of the cohort. So here in the kind of a different area of brain imaging, schizophrenia, psychosis, Alzheimer, and so on, psychiatric diagnosis. So you see the size of the cohort, which is on the x-axis here, as you know, if it becomes larger, accuracy of prediction becomes smaller in general, which could be, like, you know, sort of like a cross-validation hacking problem. It could be some other possible problems, but which means that this area of the work is not immune to that problem. So in a couple of years ago, my colleague Tristan Glattard, you know, and myself and Madeleine Sharp at the Neuro, we embarked in a study that were trying to reproduce or replicate a bunch of results in the Parkinson, the linking Parkinson disease and T1 imaging. And after a few years, and not an easy kind of study, we found out that it was super hard to replicate those 10 or 12 papers that we were looking at. Like it was in a review paper. We looked at all the papers in that review paper, and we look at and try to replicate those papers or reproduce those papers. It was super hard to actually, even if we had, like, you know, the database, like for PPMI was the database that we were mostly using, so the Parkinson Progression Marker Initiative, it was super hard to find the same cohort. That was one of the reasons where we failed. We couldn't find exactly the same cohort. The database has changed, the API has changed, like, you know, bunch of things have changed. It was very hard to actually replicate the pipeline. Super hard when the pipeline was not provided as code or as a container. It was almost impossible to replicate the pipeline. There's not enough information in the paper to actually do that. It was also hard for the statistical analysis aspect, and if there was a machine learning problem, then, you know, we couldn't find in general the same kind of accuracy that was reported in the original papers. So it's a tough experiment, took a long time, and many students. And the results are kind of worrying to me. It's not like, they're not like a 0 or 1, they're kind of a gray-ish results, but they're very, not fantastic for sure. In my own lab, we also try to replicate a meta-analysis on the essential tremor aspect of things, and using various pipelines, because we kind of were aware of that, pipeline sort of a flexibility problem, and we couldn't either. Also, that meta-analysis we couldn't replicate either. So there's a bunch of things like that. That sounds like, they are not very popular studies, by the way. But I think they are important. So we're trying to, do that. So why is the meta-analysis such a problem sometimes? So this is an interesting plot that you might find it funny. It's the Z distribution of it's a distribution of the Z values that you find in the literature. So obviously there's a bit of a gap in the middle of that distribution, and that is simply because either papers are actually not published, because that's what is called the 5-drawer effect. Do people know what the 5-drawer effect is? If you don't know, please raise your hand quickly. Okay, another good half. 5-drawer effect is the following effect. You've got a master student who's embarked in a study. You do the study. You find that the p-value after the 3 months or 6 months study is 0.23, and then thinking, okay, what am I going to do with that study? Am I going to sort of fight with reviewers and things for things that are not? Or do I put that in a drawer and forget about it and go to the next study? So basically, it's the bias that we have in the literature that significant results are published and non-significant results are not. Therefore, when you estimate an effect size across in the field, you have to think of that you have done that filtering, and therefore all the studies that may have looked that are not significant will have some problems. So that's, I think, is one of the curse of meta-analysis. There are ways of, correcting for that, but not easy or very well applied. So I'm going to talk now to make a bit of a shift of a paradigm that we would like to push. And the paradigm shift is like, we have gone from a kind of small study to big studies, for sure. But it's very hard to reuse the big studies concurrently. I think that's I'll move to that very quickly. But so I think we would like to go from silo data banks to consortia aspects. And also, I have to say that there seems to be like a rise of a data sovereignty that is much more prominent now. So a bunch of things that used to be open or used to be available to the whole world are now getting their gates closed. GDPR for sure is one of the aspects of closing those access for sometimes very good reasons. So but basically the aspect of of available data around the world and that you can reuse is kind of getting harder and harder in some sense. So the other aspect as well is that the cleaning and the data cleaning aspect is probably the most powerful and difficult aspect of many of the work that we do, but also one of the work that is actually the least recognized work as well. So that aspect as well, we have to kind of acknowledge and think of it. So in summary, a very fast-growing literature, but with aspect of problems of generalizability or replicability in many studies that are due to sample size, due to analytical variability aspect, and also in terms of the data, silo data set and a very in general poor interoperability of things. I would say also that most of the data are what we call dark data, which is a research hospital somewhere has research clinical research acquiring data, but with no capacity to actually push those data easily out. Make them findable because of above the governance aspect, the ethical and legal aspect of sharing data, but also sometimes lack of incentive, lack of technical expertise as well. So we've worked a little bit on the neuroinformatics platform. So I'm going to describe a couple of those, and please, again, please feel free to ask questions about those. I would like to say a couple of things before describing those things. One of the things that is now strikes me as one of the most important and difficult to deal with is the sustainability aspect. So there's when you work on platforms, there's having the right the people that have the right knowledge for implementing correctly things is a high bar. It's a very difficult sort of recruitment. They always live for much better paid sort of industry. But the sustainability aspect is really the thing that we have to think a priori when we work on those things, not the a posteriori is sometimes too late. The distributed governance, I think for the sustainability aspect, one of the possible way to do, and I think the only proper way to do it, is to make it a community problem and therefore a community solution where many people are involved in many labs. So the buzz factor is not like lab buzz factor. It's like it's not like a developer buzz factor. It's more like a lab or institute buzz factor. So the buzz factor is the number of developers that you have that are being run over by a bus before the project doesn't happen anymore. So like if you have only one person taking care of one project, it's a very kind of a non-resilient aspect of that project. Okay, so we need to increase the number of labs and institutions and having a bus factor of that. And building communities and standards is one of the things that I think was. So actually three projects, but I've skipped one. One of the NeuroBagel is one of the projects that we worked on, and it's really trying to move from the large centralized database kind of systems that are still again much more prominent now to like a distributed system. So the problem of like a centralized system is that there's a heavy maintenance sustainability aspect. Changes are very hard. Computation and interoperability aspect of those things, like if you try to merge some of the UK biobank with some of the PPMI data, it's going to take you months to actually try do that. So distributed aspects, we want to make the data stay locally where they are. They have all those data may have a very different ethical and legal framework of data sharing. So what kind of DUA, what kind of those things, but of course that means that you have to base your thing on a standard, like in BITS in our imaging standards that we are using, of course. So how does it work? So before, this is like, a little work on, thinking of a infrastructure aspect. Infrastructure are very hard to change and maintain. I think that's, I have to be aware of that. They're also hardly competitive space. And they really only notice when they don't work. Like, it's when your Wi-Fi doesn't work that you notice that, the hard work that is behind the Wi-Fi working like that. So, I think one of the things that we've tried to solve is that interoperability problem between data sets. So for BIDS is definitely our standard, but if we look at the BIDS metadata, it's hardly like, it's often recommended metadata and not like, constrained metadata. So finding and merging data sets, even if there are BIDS data sets, which is the best we can do at the moment, is not an easy task at all. So if you look at, for instance, the top 30 values in participant files for column containing hand. So like, if you look at, what the handedness in certain data set in the Open Neuro data set, okay, which Open Neuro is the best that we can have. It has all the formal, it has to be bit to go into Open Neuro, so that's the best we can do. But you see like all the sort of things that you can have in those files across all those data sets in Open Neuro. So anyways, like look at that yourself. It just means that if you wanted to co-analyze those data sets in Open Neuro looking for handedness, you'll have like you'll have like X weeks of work on to actually merge those things in a proper way. So what we did is to actually, Seb and his team in the lab, is to actually look at, a capacity to say, okay, if I'm on the left, I've got my Excel spreadsheet, my TSV file, that has a diagnosis, and those are the values. And I'm on the right, another group somewhere in the world that has, a column called group, and with 1, 0 things. Then, you have like, to have a way of saying, okay, that PAT thing is actually Parkinson's disease, and this group, thing 2 is actually also Parkinson's disease for some reason. And so linking that information and annotating that information locally is the tool that, so here we use Summit CT for the diagnosis aspect. And that's how it's done. We've like using a little web interface where the data don't move at all, but you just annotate those things by painting. So, oh, this is column, diagnosis. This is sample ID. This is the MOCA column. This is whatever. This is sex, for instance. And oh, by the way, within sex, 0 is actually male and 1 is female, or M is, and so on. So you actually annotate, and that's quite fairly easy and quick to do because of the work on the GUI aspect of that project. And then once you've done that, you can create little little database graph database. So those are like graph DBs here, and then send queries to all those things in a homogeneous manner. So this is basically, this is the technical aspect. I'm not going to go in the details of that, but basically you have like, you have your local graph that is not directly connected to the data. So you can actually separate the metadata and the data well, and you can search across metadata across different places in the world. So for instance, here, like, you cross, search open neuro and the QPN and the PPMI, and maybe, and there's like, and now we have a bunch of nodes across eBrain CISO node and so on. So that gives you, okay, now I can, from that query, I can see that there is 14 subjects of 23 in that specific place somewhere in the world. And I've got, 140 subjects in the QPN dataset out of 260 that are matching those things. So you can recreate cohorts across the world with different, across the metadata. Whether the data are actually available or not is another layer of things. So maybe I have that, so the interface also is kind of tuned for legal and ethical aspects. And then, you can actually say, hey, I'm not going to answer, I'm only going to answer yes or no have data. That's the first thing. And then, depending on the legal aspect of the ethical aspect of the data, you can actually share more and more. And if those data are CC0 licensed data, like is in Open Neuro, you have the capacity through the Data Lab project to actually retrieve those data directly through the results of the query. So it adapts to the capacity of the sharing and the ethical framework. So this is the bunch of nodes that we have in the world. And Open Neuro itself, actually, you can actually query through NeuroBagel the Open Neuro dataset itself, because they are now harmonized with those tools, and that's and then you can get the actual number. NIPOP is a different beast. It is really what I would say is like, I mean, Nikhil and Michel Waff, are the kind of the main authors of it. There's a bunch of people involved, but they say it's a dry lab protocol. So it's not like a monolithic thing. It's more like, when you have a neuroimaging study, how do you go from A to Z? How do you go from your DICOMs, and then you have the step of bezification, and then and so on and so on. So it's also a training environment. It's also a growing community. So the protocol is in terms of the capture, maybe the DICOM, CSV, the REDCap, whatever database you have, and then the moving to the bits world, and then from the bits world, like how do you organize and process your things? So we're using of course containers, and the description of those containers with like the boutique standard for like easy relaunch and provenance tracking aspect of those containers. And then, tracking what has worked and what has not worked, which is often, when you have like, a data set of 200 or 300 or 1,000, subjects, how many of those process pipelines have worked on that data set is absolutely crucial. But when do you relaunch and all those things? So it's all those organization level and how do you extract, features out of those pipelines results. So that probably is more like a specification and a tool around that specification. It's kind of like a bit extension to a bit study, which is not only a bits data set, it's also where are the containers, where are the results, where are the bits derivative, where are the, how do you organize the Tableau data that are not neuroimaging and so on. So it's kind of a much more general specification and a tool to actually work on that, to help you with that specification. So at the end of the day, your file system will look a bit like that. But this is like, this is the result of a NiPoP init, reorganize, bidify, run, track, extract, kind of a high level commands that you kind of follows that protocol aspect. This is like, there are little tools that help you. Okay, these are for instance, the N subjects that have failed in that specific pipeline. This is like, and so on. One thing that has happened recently is that the Enigma PD working group, which is like 35, 40 sites that are working on Parkinson, actually I've adopted that framework of processing and also neurobehavioral finding data, and now we can look at what are the subjects that have like the available pipeline, for instance, of like a fMRI prep. Let's say how many of those subjects have been processed by fMRI prep across all those nodes that are not specific, that are not centralized. So the capacity now of finding process data across different nodes that are not centralized has come up with neurobehavioral, specifically in that Enigma PD working group. This is the NiPoP sort of a leaderboard where all these sites are showing where they are with wet data and so on. And this is the adoption of the projects across the world that has, it's gone quickly. So we have an interesting link between those two projects. NiPoP can give you, what is processed and so on. It gives also the organization on the file system aspect, while neurobehavioral gives you the semantic aspect of what is age, what can I find, MoCA, can I find sex, like how do I define a cohort on that data set? So that's an interesting sort of interplay. So the thing that has happened recently is that we are now using those two things to do federated learning. So basically, in a very kind of a high level kind of a idea aspect, with NiPoP, you have the capacity to understand what is on the file system and the logistic aspect of launching a pipeline and so on. And with neurobehavioral, you have the understanding of the semantic of that data set. What is what in terms of the ontological aspect. And then, using FedBiomed, which is a well-established tool to do federated of, like working on a plan of training across data set, we actually can do now a much more easy way of doing federated learning across data sets. I'll skip the acknowledgement of the various communities that were involved in that, but I want to show a couple of results on the federated aspect, federated learning. So this is an early work, and I apologize to Michel because this is not the latest slide of that, but that looking at PPMI, ADNI, QPN. So with predicting diagnosis, whether it's a PD or AD, with sex, age, and some of neuroimaging variables, or predicting cognitive decline, whether using MoCA or MMSE, or predicting age with like the usual T1 image information. So this is the model setup, and the thing that we wanted to look at is whether what if how much are we losing in terms of prediction accuracy when you're doing federated learning compared to like mega analysis? What if you could actually gather all the data in one place, and how much would you lose in that aspect? And I mean, the result is that we don't lose that much, and actually sometimes not at all. So I won't go into the things, but brain age and cognitive decline, depending on which data set you're learning on, you don't actually lose that much on the performance at all. So this is a kind of a summary of those results. where like, siloed definitely you lose. There's, you don't actually generalize well when you train on one specific data set and apply the prediction of on others. But you don't actually lose that much when you actually do that with federated learning compared to like a mega analysis aspect. So take home message. I don't know what's the time, but I'm sure it's time to. I was a bit short, but it's okay. Take home message. I think what we try to do is much more building communities of practice with the tools, and that those tools should not be like a one lab tool. Like those tools are really have to be community tools, and therefore the governance of those things has to be distributed as well. So that's a bit sustainable. We also try to build the things that are cheap in a way that they're simple and not based on like as a simple technology as possible, and also sort of adapted to the communities that are going to be used. Using them. Avoid the locking issue. I think that's important. What if, let's say, those tools are not maintained anymore? And you have, before you're adopting something, you have to think of let's say the worst happens. The two maintainers of that project are actually doing something else with their life and are gone. What is left on your disk and all things like, and I can tell you sometimes when you are, with let's say a big database thing that is maintained by someone else, it is going to be super hard to recover the information that is there and to reuse those information. So everything that we do is basically adding more like, data dictionary aspect. So let's say NeuroImaging doesn't exist anymore. What you left is all the data plus the data dictionary that you have on the top of that. You just don't have now the nice interface that query across things, but that, is or you could possibly have that, using the CLI, but I'm hoping you don't lose at all anything because there's this is a specification, and actually what you by adopting that project, you're adopting also the community, and you're participating with the community of people who have adopted that project. I think that's a bit like BID. It's really the extension of BID in my mind. So transparent and distributed governance, I think that's a key aspect of those things. And again, build community of practice. Consider all the incentive. I think this is a quote from Carol Goebel from in the UK that says that we have incentive as love, fame, money, and rules. And I like that quote very much. I think we work because we love the thing we do. We also want to be recognized, and that's kind of a classic incentive in academia in particular. Money, of course, and rules because maybe your institution is forcing you to do something on the data sharing aspect, and you have to do it, and that's it. So we have to work on building those communities of practice, having those kind of incentive in mind, and not only the that's it. Thank you for your attention.